This video focuses on strategies for interpreting structural information by adding proton-proton correlation spectroscopy to the other data that's been described so far in these videos. The acronym COSY typically refers specifically to the proton-proton correlation spectroscopy experiments, although there are many other types of correlation spectroscopy. In short, the correlation involves varying an evolution period between two pulses, the T1, acquiring a relatively large number of spectra. The textbook describes 2 to the 4th power, or 16 spectra, with the data typically plotted in the corresponding way. This spectrum shows two axes by frequency, F1 and F2, as well as intensity of the signal, which could be integrated. Typically, this three-dimensional plot on the left is viewed as the two-dimensional plot without an indication of intensity, but that is separately obtained in a traditional one-dimensional spectrum by integration of the intensity of the proton resonances. This is the plot for a single resonance for the entire spectrum of a compound. We will plot the spectrum on a square. The diagonal is the one-dimensional spectrum without intensity, and then the cross peaks indicate all of the protons that are coupled with each other. The cross peaks should be reflected across the diagonal. Any deviation from this reflection may indicate noise, and that gives us a clue that we may be able to ignore some peaks if they are not reflected. Traditionally, the COSY experiment is presented as the first of the two-dimensional NMR experiments. But in practice, I recommend first finding the one-bond correlations between protons with the respective carbon atoms, such as the HMQC experiment, which was described in a previous video. What is truly valuable about doing the HMQC prior to the proton-proton correlation experiment is that if we know that two chemically non-equivalent protons are attached to the same carbon, that provides a great deal of simplification in deconvoluting the proton-proton correlation experiment. Once we've obtained the data from correlation of protons with carbon-13s being uppercase Roman letters, protons being lowercase letters, then we can better evaluate the COSY spectra. So I will recommend having this table from HMQC at hand as you analyze the COSY spectrum. Due to the complexity of the spectra, I recommend using expansions liberally when you're examining the spectra that you've obtained yourself. And I will try to provide those expansions as much as I can when using spectra from the textbook or from the literature. This is an expansion of the alkene region, which allows us to distinguish B from the cluster of peaks C, D, and E. From this correlation, we can see that A is correlated with B and with D, although D does overlap with E, so we need to keep that in mind. We can also see that B correlates with D. This is where having the HMQC data beforehand is valuable. The correlation of proton B with proton D is not surprising because we have already established that both protons B and D are bonded directly to carbon D. And since we now know that proton A is correlated with B and D, and we earlier established that proton A was bonded to carbon B, we can claim that carbon B is bonded to carbon D. And then we can apply some logic based on the chemical shift of carbon D and the attached protons B and D, being consistent with an sp2 hybridized carbon D. If carbon D is sp2 hybridized, then there is not room for any other bonding pattern other than a second bond between carbon D and carbon B, assuming that there is not a long-range interaction between these atoms. I have shown a dotted second line to indicate that this is a likely claim which may be strengthened or refuted with additional evidence. There is a weak correlation between either D or E with both G and H. This is a weak correlation, so I won't make too much of it yet, but I'm reminded that protons G and H are attached to carbon G. First of all, we can see that proton F is correlated with protons G, H, K, and L. This may seem like many correlations, but then if we remember that proton F is bonded to carbon E, protons G and H are bonded to carbon G, and protons K and L are bonded to carbon F. We know that carbon can have a maximum of 4 bonds with other atoms. And so that leaves us with the only possibility, again ignoring long-range couplings, for the bonding pattern carbon G bonded to carbon E bonded to carbon F. Based on the chemical shift of carbon E and proton F, and knowing that the formula has 1 oxygen present, it is reasonable to claim that the oxygen atom, which I will color in as O, is bonded to carbon E. In addition to confirming that protons G and H are coupled, as they are chemically non-equivalent but on the same carbon atom, carbon G, we can then look at other correlations. For example, I is correlated with K, L, and M3 and or N3. K is correlated with protons F, I, and L. Proton L is correlated with protons F, I, and K. And then we see that the M3N3 cluster is correlated with I. We know that proton I is bonded to carbon H. Therefore, carbon H is bonded to carbon F. Finally, with the correlation of proton I with the methyl groups M3 and N3, which we know are respectively bonded to carbons I and J, we complete one end of the compound, and we know that we are at a terminus because carbon can be bonded to no more than 4 other atoms. In summary, we've established 2 spin systems of carbons B and D, which we suspect are an alkene, and 6 more carbons, E, F, G, H, I, and J, with E attached to an oxygen atom. What remains is to determine how these 2 spin systems are connected to carbon C, which has protons C and E, and to carbon A, which has no protons attached to it. For that information, we need another correlation experiment, which is described in the next video.